So let us return to concrete calculations and have a look at a second example where we can actually see how second-order perturbation theory works in practice. This starts again from the harmonic oscillator, but now we assume that the perturbation amounts to an extra constant force that displaces its equilibrium position. The perturbation, the corresponding extra potential energy, is then linear in position. So including this term, the potential looks like this. Well, this can still be written as a parabolic potential, but it is now displaced both in energy and position by amounts that we denote by a tilde. We can determine these displacements by writing the potential in a general form, which centers it at its minimum, and then compare these two expressions for the potential. So as the potential is still parabolic, we can just solve this problem exactly. The energy is just changed by the displacement of the potential, and the wave functions are shifted in position to be centered on the minimum, so on the new equilibrium position. But now we see that the energy is shifted by an amount proportional to lambda squared. So therefore the first order result in perturbation theory should vanish. Well, according to our main result, this contribution is given by the expectation value of the perturbation, evaluated in the original unperturbed eigenstate. And indeed, this involves the expectation value of position in the ground state of the original quantum system, the harmonic oscillator with the potential centered at the origin. And we have seen that for this expectation value vanishes. So now, including the second order, we have the approximation given here. In general, this expression involves all the other eigenstates of the system and their energies. Fortunately, in the present problem, it simplifies a lot when we then have a look at the matrix elements of the perturbation. Only a single matrix element turns out to be finite, so we are really fortunate here. You see this when you recognize that x times the ground state is just proportional to the first excited state of the original system. X is just the first Hermite polynomial with a suitable proportionality constant C tilde so that all states remain normalized. And because all these eigenstates are orthogonal to each other, this just vanishes unless n is equal to 1. And then this expression simply becomes minus C tilde because of the normalization of the states. Now we could just read off C tilde from our general expressions for these states, including the normalization factors. But here we can also obtain it directly in the following way, namely by reading the definition involving C tilde backwards. And then you see that it is just determined by the expectation value of x squared in the unperturbed ground state. This is of course again just sigma squared, as we have seen so many times before. So this fixes the numerator in the second order expression, and the denominator is just the difference between the two adjacent states, the ground state and the first excited state, which is just the negative of h bar omega. So if you collect all these results, the approximation for the energy including the second order term becomes h bar omega divided by 2 minus lambda squared divided by the square of 2m omega. And this coincides precisely with the exact result. One can indeed check that all higher order corrections to the energy vanish in this simple example. Now in general, perturbation theory will not give you an exact result in a finite order, if it converges at all. But it still works well in many quite general cases. So for a third example, let us have a look at a somewhat more general setting. Let's consider physical systems whose dynamics is well approximated by harmonic oscillations. Examples would be the vibrations of molecules or of atoms in a solid. Such oscillations appear so frequently because they describe the motion of a particle close to an equilibrium position. That's the position where the gradient of the potential vanishes and the local curvature is positive. It is then natural to describe this situation by expanding the potential in a Taylor series around the equilibrium position. The linear term vanishes by the definition of this position. Up to second order, we then obtain a shifted parabolic potential, as in our previous example. This will already serve us well in many practical situations. And beyond this, for illustration, I also include the next non-vanishing term of the tail expansion, let's say of order k. So the energies of this system would be similar to the displaced harmonic oscillator, which we now take as our unperturbed system, as we can still solve it exactly. And then we could include the next leading correction given by the first order in perturbation theory. This is just an expectation value involving the displacement with respect to the equilibrium position, a higher moment of position, evaluated in a state of this displaced harmonic oscillator. You can calculate these moments exactly, and I have specified this here for the ground state. Recall how we took parametric derivatives to get the second moment of position from the Gaussian integral. You can just keep repeating this trick. But this is actually finite only if k is even. So if k is odd, you have to be careful. The correction is then either given by a higher order of perturbation theory or a higher even term in the tail expansion of the potential. And generically, the first term in this expansion here would be k equal to 3, unless the potential is reflection symmetric, so that all terms here must be even. Now, these considerations can be used, for example, to get an estimate for the anharmonic motion that results in the thermal expansion of a solid. But again, they can also tell you something more general about such systems, for example, about the role of spatial symmetries. Now, this sketch here also highlights the limits of this approach. Indeed, notice that the sketched potential also allows for tunneling, which turns out to be a non-perturbative phenomenon. As a matter of fact, there is an ingenious way to describe tunneling by expanding the potential about a maximum in the classically forbidden region instead of a minimum, and then replace time by an imaginary time, a so-called Wick rotation. Just recall how we found that the momentum is effectively imaginary in these regions as well. I just mentioned this to emphasize that not all is lost if this approach breaks down, and for the case that you would like to do some further reading on such advanced methods. So to summarize, as you can see, perturbation theory is a rather systematic approach to describe systems that are similar to some well-understood system, really to calculate approximations for the energies and states of such systems, based on a small additional contribution to the Hamiltonian, which we call the perturbation. So this could be used to relate somewhat more complicated systems to simpler variants, but also to simply study the response of quantum systems to external probes, which is just as important as an application. And besides aiming to get some accurate estimates, this approach really also helps you to understand the mechanisms by which a system responds, such as illustrated by our main result, which involves an expectation value of the system, so you can actually determine such expectation values from an energy shift. All of this shows you that this simple result in itself already has a wide range of applications. And when we looked at the second order result, we could draw many general conclusions about the behavior of quantum systems, to estimate when perturbations become strong enough to totally change their behavior, and uncover the role of level repulsion and degenerate levels, which both tell us something about symmetries of a system. So one should not think of this method as just a way to get some possibly poor approximations when you really want to have some exact results. What this really does is to help you to identify what is actually going on in a system. It helps you to separate the physically meaningful mechanisms away from aspects that are mere details. Indeed, physical phenomena are often organized in terms of hierarchical scales, of times, length, energies, and so forth, that tell us which effects are really relevant. And you could spend much time on finding an exact solution of a problem when it turns out that it does not apply to the meaningful ranges of parameters. As for an outlook, recall that what we discussed here is a particular setting, namely that of stationary systems, for which we focused on the energies and associated eigenstates. Now you can use this approach also to calculate other quantities, and the general idea of perturbation theory can furthermore be extended to many other settings. In this course, we will later study time-dependent problems, where we will use another variant of perturbation theory to calculate the rate of transitions between different energy levels that then occur. And looking beyond this course, there is a general framework of linear response theory, where you encounter so-called Green's functions as powerful mathematical objects, for instance, to describe the propagation of particle-like excitations in your system. These could be these electrons with modified properties in a semiconductor that I mentioned briefly before. And with this general language, you can also study superconductivity, where electrons form effective particles known as Cooper pairs. And as it happens, many fundamental theories in physics can only either be evaluated or even formulated by using the language of perturbation theory. Quantum electrodynamics is such an example, where you can use Green's functions to describe the propagation of bare particles and use Feynman diagrams to expand the interactions in order of the fine structure constant alpha, which actually turns out to be not really a constant when you try to make the theory convergent across all energies, reflecting also that the bare particles you start out with aren't the particles that you observe in physical experiments. So as always, physics is really interesting when you apply these powerful concepts to the complex world around us. And to really get there, we move on to the next part of this course and have a look at quantum mechanics in 3 spatial dimensions.